Dear participants, welcome to the third day of our FDP program. And first of all, sorry for the technical issues we faced. And now we have the today and tomorrow we have the hands-on training and session and case studies with the simufact solutions. Now we have joined with the simufact members, Ratish, as well as technical person, Mr. Anand Padmanabhan. Let us give a short intro about Mr. Anand Padmanabhan and we'll go to our session. About the research person, Mr. Anand Padmanabhan has 12 plus years of experience in at CAE, CAD, simulations, etc. He is having specialized on structural simulation domains and he have a bachelor degree in mechanical engineering from BTU University, Karnataka. He is an associate with the technical supports and training activities for Hexagon MSc software product solutions like nonlinear analysis studies, simufact, MSc Nastron, MSc Mark, various organizations, team members of those who are from design, production, tool making, and engineering to set up CAE process. He having wide knowledge in technical upskilling, handling POCs, and has concluded several key projects. He also delivers several corporate training for major Indian automotive, aerospace, and manufacturing customers. With this short introduction, I'm handing the session to Mr. Anand Padmanabhan. Please participants join with him. If you have any doubts or clarifications, you can clarify with him at the end of the lecture. And followed by this lecture, we have hands-on training in the CAD lab. So online participants, you may watch out how we are going to proceed further steps. Thank you. Now I'm welcoming Anand Padmanabhan sir to take the lecture.
Thank you, sir. Thank you for the kind words. So very good morning to everybody. And sorry for the interruption due to the technical problems. So we shall start slowly. I hope you can see my screen. So I'll just go to the slideshow view. So once again, welcome to the session and very good morning to all. So my name is Anand Padmanabhan and I'm handling the technical team at Solace India Technologies. So our topic of today's discussion would be simulation of metal-based manufacturing processes and using the software called simufact actually. Okay. So to start with it, I will just give a brief introduction about the company Solace India Technologies and followed by the simufact. Then we'll start into the software related discussion. So basically, to start with it, what is Solace India Technologies? So basically, we are services and solution providers in CAD solutions as well as CA solutions all over the country. And basically, if you talk about CAD or PLM technology distribution, we are a leading partner with Dassault Systems India. Basically, if you've known CATIA or 3D Experience Technologies, we are the solution providers for these CAD and PLM related technologies actually. So, and coming to CA technology distribution, like we are the partner with MSc software. Right now, it is under the company called Hexagon and VA grade actually. And most of the initial we started with most of the customers will be knowing us through the Nastran software. That is MSc Nastran, which was the first CA tool almost used by major OEMs, and it started its inception during the NASA moon landing actually. So we are well aware with the Nastran tool. So we are the technology providers as well as the training partners with MSc software as well as Hexagon actually. And apart from the you can say the software providing and solution providing, we also offer engineering services, offshore engineering services for CAD as well as CA services from India to customers all over the world actually. Okay, so our head office is in Bangalore, in Hebbal, and we have our offices in Pune, Hyderabad, Chennai, and New Delhi, and these major, cities in India, actually. Okay. And at Solace India, we help our customers to solve engineering problems and through world-class solutions comprising of digital tools, consulting services, processes, and sharing, as well as providing knowledge and skill, actually. So mainly, we are trusted partners for automotive, aerospace, defense, and various other engineering industries, as well as academic and R&D institutes. And as we are business partners to companies like Hexagon, BA Grade, Dassault Systems, and Toray, actually. Okay, so we have over 30-year-old customer-centric organization, and we have over 1,000+ customers, and partner for solution in product design, validation, and manufacturing. So this is a brief introduction of who we are, like from Solace. And
what is V grade and you are going to explain that?
yes,
What V grade and Toray do?
yeah, VA grade and Toray is for VA grade is for MBD and multi-body dynamic simulations, huh? Yeah. And Toray is for mold flow and things like mold flow software. And coming to the the MSc, that is the global MSc product portfolio, and from materials to systems, basically. Okay. So right from our material aspects to system aspects, we have solutions. So for example, if you are talking about parts or assemblies, or if we are talking about system related simulations, okay, we have the end-to-end solutions for all these aspects, actually. So if you talk about, for example, fabrication, like if you are doing forming or additive manufacturing, we have specific solutions for this area. And if you're talking about assembly, like welding or joining simulations, we have specific solutions like simufact welding and simufact joining. Okay. And coming to systems, like, for example, we have the solution like NASTRAN for structural analysis, and there is SE Flow, SE Tetra for CFD related solutions. And there is ADAMS for multi-body dynamics, and then ACTRAN for, acoustics simulations, actually. So it's a end-to-end solutions, what we provide to the customers. So mainly today's discussion will be based on the manufacturing. So we'll be concentrating on the product called simufact, okay, which comes under the manufacturing domain as a solution, which is offered by the MSc Global Portfolio. Okay. And let's get an introduction to the simufact. And if you have any queries, you can interrupt me. We are we are in an open discussion. That is very much fine. And we'll start with the introduction to the simufact software, which is mainly used for the metal-based manufacturing solutions, actually, which is an end-to-end solution for metal-based manufacturing simulation. It can be in the forming or forging domain, or additive manufacturing domain, or joining processes like welding, and so on and so forth, actually. Okay. So how did the simufact software come into the picture, which was used for the manufacturing simulation? That is the introduction. So simufact is basically a German based solution. It is a German company, and simufact, as the word, it starts for simulating manufacturing. Okay, so these two words starts. It is the word simufact comes from these two words, actually, and it is basically supporting the metal-based manufacturing processes, and it is a very much manufacturing-oriented process simulation, actually. Okay, and it was headquartered in the Hamburg place called Hamburg in Germany, where the development of this solution started. And technology-wise, it is using the well-known solvers like MSc Mark and MSc Ditran solvers, which is working in the back end behind the simufact for solving the complex multi-physics as well as the multi-structural problems, actually. Okay. So simufact was founded in 1995, and as I told, as I explained, it was headquartered in Germany, and it offers solution for large number of manufacturing solutions in the metalworking industry. And it is providing software products and services for optimization of manufacturing techniques by means of process simulation. Okay. And in 2015, it got acquired by the MSC software company, which is a part of Hexagon actually. Okay. Hexagon is a global provider for information technologies that drive productivity and you can say quality support for geospatial and industrial enterprise applications actually. So all these things comes under the solution provider called Hexagon, which is handling these solutions actually. And we are coming under the manufacturing intelligence division of Hexagon actually. Okay. So simufact is a part of this technology providing. And at a glance, when we look at the simufact product or the solution provider, we broadly classify our solutions in forming domain, additive manufacturing domain, and welding domain actually. Okay. So in forming domain, what are the different analysis we can do, or what are the different processes that we can perform? So we can perform cold forming, we can perform hot forging, sheet metal forming, or any of the rolling processes, ring rolling processes. It can be pressure welding or heat treatment processes. So all these processes we'll be able to perform under the module called simufact form. Okay. And coming to the welding, we can do the arc welding processes, laser beam welding processes, electron beam welding, and you can see brazing simulations, as well as for automotive customers, we can very much do the resistance spot welding simulations. And there is a direct energy deposition, DED process, which is the deposition methods which we can do based on the arc or laser based deposition processes we can able to do through the direct energy deposition actually. Okay. So this is some kind of additive manufacturing processes, but we use the welding technology to perform the additive manufacturing. It can be arc based or laser based kind of process actually. Okay, cladding, laser based cladding, or you can say arc based deposition process, or they call it as DED process, actually, direct energy deposition. And coming to simufact additive, additive is basically metal based additive manufacturing processes. Basically, we know this is an upcoming technology which is being looked at in the industries as an upcoming technology, mainly the powder bed fusion technologies. So in powder bed fusion technologies means it can be SLS or SLM or DMLS method. Okay, these kind of technologies actually, direct metal laser sintering, directly melting or sintering processes. So all this comes under the additive manufacturing process, metal based additive manufacturing. So simufact will be able to handle these kind of processes actually. Okay. So this is a simufact at a glance. Now let us deep dive into the simufact further. Like what is simufact welding, what is simufact forming, and what is simufact additive actually. So today we'll be covering the welding aspects and followed by the forming. And tomorrow we'll be having a session on simufact additive manufacturing. Okay. So let me start with a overview of the simufact welding, and we shall see some case studies and then followed by a demo of the software. So we'll see how it goes actually. Okay. So coming to the overview, like how simufact welding came into the picture, or why such a software or why such a technology is required in the market in the manufacturing industries. So basically, the idea was born from simufact welding from 5 of these top OEMs like BMW, Audi, and these OEMs. They started. They wanted a solution to make the process or simulation process much easier for them. Actually. Basically, these are all FA related technologies, finite element based technologies. But how we can make the finite element technology easy for the user actually? Okay, who might be a design person or might be a shop floor person who might be working in the industry, but who might not be aware of the finite element technologies, and how we can make use of these technologies, and how we can reach out to the people who are working in the shop floor or in the manufacturing domain. So that was the idea of starting a simulation software for the manufacturing people actually. Okay, so in the sense it should be the software should be innovative and it should be user friendly too. That is the main aspect. It should be able to any person who is working in the industry should be able to understand and should be able to easily set up his process in the software and then find the solutions for his problems actually. Okay, that was the idea. And close to real manufacturing. So whatever solution or whatever manufacturing issues that are there, we should be able to simulate that in a very close format actually. And then it should be supporting the best solver technologies in the market. So backend solver should be robust. Then only we will be able to find closer solution to our problem set. And dedicated to welding applications. So these automotive customers or aerospace customers, they wanted the solution which is dedicated to the welding applications. Okay, so it even though it is a a finite element tool, it should be dedicated to the welding applications or forming applications. That was the idea of starting a project like a simufact actually. Then over the years, it started in 2005. Over the years, it started evolving and new technologies started coming into the picture. Like they started with the the arc welding, laser beam welding. Then they started introducing the resistance spot welding technology. Then followed by some improved GUI based applications to the software, so that the user will get a direct feel of whatever the GUI. If the GUI based application is there, we'll be able to easily set up our models inside user interface actually. Then the direct energy deposition, when the deposition technologies or the additive manufacturing came into picture. So they started developing this kind of technologies into the software actually. Okay, so this is the basic overview of the simufact welding, how it came into the picture actually. Okay. So now coming to the manufacturing, like what are the problems that is mainly faced by the manufacturers? It can be the joining technologies, or it can be the forming technologies. Okay, so to make for example, to design and optimize basically the welding strategy and basically how to reduce the weld distortions actually. So this is the in the industries they might face these problems on a daily basis. So how to overcome these kind of problems actually? So it can be by identifying the best welding process, or optimize our fixtures or the clampings or the clamp concepts. It can be geometry based or time dependent force, or these kind of time based release or force or stiffness aspects which are come into the clampings. Okay, or optimize the order of the welding path. So welding trajectories or welding path based on the sequence of the welding, how it can affect our distortions actually. Okay, and it can be optimizing the heat source parameters. So all these aspects come into the picture when we are doing a welding process actually, and how we can overcome welding distortions and other related problems when we are trying to and how we overcome using optimizing these parameters. Okay, to calculate residual stresses on the components. So residual stresses also can be a major issues when we are talking about welding processes, and understanding how weld input parameters affect the welding process actually. Okay, and then it can be prediction of welding parameters, then prediction of optimum clamping positions, clamping loadings to reduce distortion actually. Okay, and it can be we can study the heat affected zone or the weld depth penetration. So these kind of studies can be made. So if you see here on the weld macro graph, you can see the the weld penetration or the fusion zone, or how we can model this fusion zone in our software, and we can see the heat penetration, or whether the heat is whether the fusion is happening, or whether it is a burnout is happening at that area. These kind of things we can study actually. Okay. And further, if you go further deep dive into these things like mechanical properties or microstructure in the heat affected zone, those kind of studies also can be made. And other thing will be temperature field, calculation of the temperature field. So if how the heat distribution is taking place in these areas, or whether we can optimize those parameters, or those kind of things can be studied. So 8 good reasons to employ the simufact welding. First would be to identify any critical distortions in the components or in the assemblies, to investigate clamp tools, to investigate the welding directions and welding sequence, to investigate the influence or unclamping and weld distortions and residual stresses. Okay, and development of heat affected zone. Okay, and then can be planning of welding processes. Then all these aspects are, if we are dealing with any of these kind of aspects, we can employ softwares like simufact welding for our applications actually. Okay. So what is the basic agenda? Like it can be, you can say, saving the time and money by testing our processes in a virtual environment. So basically in the industries, they spend a lot of effort in testing and trial and error method to arrive at optimum parameters actually. Okay. So if we are able to reduce our shop floor tryouts or the real testing which is going on, we can employ these kind of simulation technologies during the design process. During our design process, we can verify your design before the trials actually, or before you are going for a test, to identify any possible problems which can happen, or test new designs without which usually not tested because of short budgets. Okay. Then during manufacturing process, to investigate any manufacturing related issues, to get inside look of our process and to optimize basically. So main focus would be the distortions and study on stresses which can happen during the process actually. Okay. So here we can see an example, like multiple ways to use the simufact welding in our simulations to find our way and to overcome some kind of challenges actually. So mainly here you can see a component. So studying the influence of different weld sequence basically. Okay. So based on different weld sequence, you can see the first weld sequence on this, you can say starting with 1, 2, 3 and 4. So this was the first weld sequence in which the welding was done for this component. And then we will follow another weld sequence like 1, 2, 3 and 4 actually. Okay. So these different sequences or these different trials will give out different outputs. It can be with respect to distortions, or it can be with respect to the residual stresses outputs actually. So mainly if we employ these kind of different welding strategies, we can see our distortions will vary drastically actually. Here you can see distortion is around 1.04 mm. It has come down to 0.75 mm just by changing our welding strategy or welding sequence. Okay. And also we can study of sequence for different weld path. For example, this is a car door assembly which is welded. And here you can see if you use a continuous weld or a discontinuous weld or a staggered weld like this, how the distortions at the end can vary. Even though the pattern is same, the magnitude of the distortions might be different actually. Okay. So these kind of studies can be very much successfully done using the simufact welding software. And another case study here we have, there is a studying the influence of different clamping position. So this is like a finite element model of components, and here we can see the clamps which are there on the components actually. So these clamping geometries has a influence on the welding results actually. For example, if we change the clamp locations, for example, here you can see they have placed the extra clamp to reduce the distortions at that particular area. So we are able to reduce the distortion on that particular location section. Okay. So this used different CAD based geometry based on experience or simulation based results actually. And using simulation results to adjust the clamping positions. Okay. So these kind of studies also can be done using the simufact. And then comes something like we may have components where we have different welding directions we want, welding sequences, okay, and pre-bowing effects we want to incorporate, and number of welders and heat input. So there are different parameters will be there actually. Okay, out of these different parameters, how do we find out the best parameter? It can be, you can say 2 robots or 1 robot, you know, with using the pre-bowing effects, or using some kind of reverse welding technologies, or you can say changing the welding trajectories. So these kind of things, if we want to do the trial and error, we can very much use the software platform to do that actually. And summary of runs, for example, we can see different parameters like pre-bowing 0 means there is no pre-bowing with 4 mm, or with different input parameters like voltage, current, your varying your velocity. Okay, all these parameters will get different results, and we can arrive at what is the optimum parameter using the tool actually. So further deep diving into some case studies with respect to the simufact forming and welding. So first one would be a motorcycle swing arm. That is, it is a sheet metal kind of parts, and then we have arc based welding, and we have the heat source optimization here actually. So this will be the welding setup. So here we can see the 2 components which are held together in the fixtures. So here we can see the fixture location where the components are held together for the welding actually. And here we can see the weld micrograph after the welding is done. So when we see the macrograph, we can see the heat penetration and then the fusion zone, and all these parameters can be seen actually. So after doing the simulations, we can see some distortions are there in the component which are coming at a particular location actually, okay, which are more than the maybe the accepted range. So here they did a study where they wanted to optimize the welding process, mainly the heat source actually. Okay. So from the experimental weld pool, we were able to see you can see the weld pool distribution here from the experiments, and the heat input that is, which was around 4,000 watts, which was used for, and they were able to find some large weld penetration, which was happening during the process actually. Okay. So this is the experimental setup, and this one will be the simulation, how we can get the, the close heat affected zone or the heat affected fusion zone, which is there in the simulation and there in the experiment actually. Okay. So they wanted to basically optimize the weld pool so that using less power, we should be able to get the sufficient penetration, heat penetration, as well as we should be able to get the optimum parameters actually. So in this study, we were able to find that using to like half of the energy, that is, first we were using the 4,000 watt energy. After that, with 2,000 watt itself, they were able to, get the optimum penetration actually without over penetration. So this helped to reduce the distortion at the end of the simulation. Okay. So we can able to see the worst result here using the, power of 4,000 watt. And once they optimize the heat penetration, weld pool penetration, we are able to get the optimized result, that is with the less distortion actually. So overall distortion in this case, it was around 0.76 mm, and it came down to 0.35 mm. So, any queries or anything anybody has?
What is the pre-bowing?
Pre-bowing is a pre-bending edge. It's a pre-bending, means it might be a distortion when the distortion happens.
Is it due to clamping the distortion?
Yes, sir. Yes, due to the clamping. So what we do is,
Building.
yes, before the welding, there's the pre-book actually. So if it is in the positive direction, we give the negative direction pre-bending. So what?
ARS.
Yes, due to the clamping. So due to optimize that, we will do the pre-bowing and then we do the welding action so that it will come to the correct position. So online participants itself, I mean, if you have any queries, you can unmute and we can discuss.
Sir, good morning. Myself, Manigandan. I am research fellow for Voltech. I have one doubt for in that second case, some best result, worst result it is coming. There, in the best result, what are the modification you modify? How the best result it is coming?
Which one, sir?
Second one, sir.
So, morning. Sir, could you repeat the question once again, a little bit slowly?
Sir, the last slide.
The last slide. Okay, we are moving, sir. Wait.
In the second diagram, there
Second diagram.
yes, best result, worst result came, sir. So in the best result, the first one, what are the modification you did? How the best result it is come that first case, sir?
Okay, sir. Yeah. So this was
You
based.
understand?
Yes, sir. So the first best result, that is the, after the optimization of the heat source, sir, actually. So in the first, experiment, they were able to find that using a, 4100 watt. Okay. That is the current and the voltage. So current used was 200 ampere actually, and voltage used was 20.5 volts. So if you get the, if you multiply this, the total, the power would be around 4100 watts. So with this trial they did, and they found out that the penetration was coming more actually. Okay. And then what they did is they tried out a trial with a lesser parameter, that is 200 ampere, and they reduced the voltage to 10 volts actually. So the, the total power, it came almost half of the initial, trial. So they were able to find with this less power itself, they are able to get sufficient weld penetration, as you can see in the second diagram. Okay. And there was no overwelding also happening as compared to the first, in the first simulation actually. So due to the overwelding, what happened is some areas, it was giving a higher distortion at the end due to some large, shrinkage effects, which can happen after the welding process. But if we reduce the heat input, or once we reduce the power, they were able to find that they were able to get the sufficient penetration as compared to the experimental value here, whatever is shown here, as well as they were able to optimize the distortion. So it came around 0.35 actually from 0.75 mm. Okay, that is shown here in the best result, what we are showing here. Okay.
Okay.
Here we can see the slide with higher distortion.
Okay, and then the experimental you taken for real time parameters, 4000 to 4100, and it
Yes,
is a real time parameter you take, and you do that simulation. Sir, first of all, you take the real time parameters.
Yes.
You applying that simufact software.
Yes.
You identify the problem. After you reducing the voltage, you rectify that problem, right, sir?
Correct, sir. Correct. That is the studies.
How to arrive at value? So starting heat input value.
Yes, sir. So that we have to do certain things called calibration in the software. So there will be calibration. So yeah. So basically we have two different analysis, like thermomechanical analysis and thermal analysis. So in thermal analysis, we will do we first create our model. We input different parameters. We change our parameters and do the calibration study until we reach a optimum parameter actually. Okay. Then
Yes. In the experimental for this object.
yes, sir. Once we do find out the result in the trial,
Fundamental value what we are already.
Yes,
That is the outcome of that.
yes,
The optimum result is applied to fundamental.
yes. Verified, yes. Yes, that's been verified.
Is any deviation you are found out actually
Deviations from
analysis and then experimental?
yes, yes. So the deviations can be like if we are, matching all the parameters, input parameters, we can well and come within the 8 to 5% deviation compared to the experiment and the simulation. That we have observed in the software. Yes. Okay.
Is this experiment what you have done? Is for some customer or it is your own study?
It's for a custom. Shall we proceed?
Yeah.
Yes.
Sir, exactly how you fix for 2000 voltage, sir? You trial and error method, so many variation you keep on the software, or you using some calculation? How you find out exactly for 2000 voltage? It is enough for to.
Yes, sir. That was done by a calibration study in the software only, sir. Actually, some trial and error we did. So, so based on that, 2-3 trials, we found out with some
Exactly.
and varying the voltage parameters and so other input parameters. Then they arrived at this particular optimum heat source actually.
Okay, good, sir.
Our ultimate aim is to reduce the distortion. For that, we are changing the parameters
Yes.
based on the trial and error.
Based on the trial and error.
Okay, sir. Thank you.
May you know the metal which is used for the experiments?
What's that?
May you know the metal which metal is used for the experiments?
Material, sir. Material, I'm not so sure. To check that actually.
Sir,
Material.
I have one more doubt, sir. Directly we will modeling for this directly in this software, or we want modeling for some other Pro or some software. We will import the file from in the software, sir.
Yes, sir. For that, for example, your CAD models or whatever designs you have modeled it can be a CATIA or ProE. All those formats are supported in the software. And also we have a tool called MSE Apex, MSE Apex actually, which is a preprocessor for the simufact welding. So in that preprocessor software, if it is like simple models, you can model in that platform itself without, you can do the solid modeling, all those things in the, which I'll be demonstrating during the demo actually. So in the,
But especially in the software we using for analyzing, right, sir? For
yes.
welding and additive manufacturing. This initially you told some application. That application we analyzing for the software. Sir.
Yes, sir. Yes,
right,
sir. Yes,
okay.
Sir. So we can use the CAD models. We can import the CAD models in step format, Parasolid format, IGS format, or native CAD formats like part or assembly files. We can import that and we can carry on the analysis. Or if you want to use the in-house CAD technology which is available inside the tool, that also you can use it. Okay, I'll be demonstrating that in our way.
Yes, sir. Everything comes from that.
Yes.
As a one word combination of that. A lot of.
SolidWorks, I would say it is mainly a CAD-based software. It has some simulation aspect to it, but here the main focus is simulation. Actually, it is a reverse of CAD. Like CAD, we don't have much, but we are focusing on the simulation, like material database, or if you want to material properties which are readily in the database, you can pull it directly and use it for a simulation. Actually, okay. And the GUI, as I will be showing you, it is very user friendly for setting up your process. Okay, that is the main USP.
This component exactly where it is used? What is the function of this component?
This component, I think, sir, it's a bike motorcycle like swing arm.
What is swing arm?
Swing arm, I think it is a component suspension kind of thing that comes in the motorcycle.
Okay, that the rare wheel holder.
Yeah, that's great.
Rare suspension.
Yes.
Modern cycles. We can find it. Modern cycles we can find it.
Yeah.
Yes.
And this also, how do you, in the functional side, whether the distortion, whatever that because of welding, is the distortion is allowed or not allowed. Suppose it's going to catch the both sides of the wheel axles.
Yes.
Okay, the distortion at this point is going to be critical. In between distortion is not going to bother much. How the distortion point of view, can you go back to this point where which point is the distortion you are aimed to reduce?
Yeah, here distortion was found out to be here at this location.
But that is not the very important zone. No? The ends probably where it's going to hold the.
Yeah, during the function aspect, yeah.
So the distortion at that point, does it matters?
Maybe because they might be aiming at some, accepted tolerance values, which will be, after the welding and cooling is done. They might be finding whether they might be, interested in reducing the distortion at that particular location so that they will get the, component within the tolerance. So that after that, if you fix it in the fixtures, might be the distortion will change. That maybe we have to go at further analysis, actually, structural analysis.
So we can check the mechanical properties also by using the simufact,
Mechanical properties, yes.
like the tensile.
Yes. For that, we might be needing some multi-phase properties. Then we can do that actually, like tensile strength,
Yeah.
distress, those kind of properties we can, yes. And then comes the next study, that is inner door assembly welding, actually, okay. So this is a laser-based welding process. So here you can see car door assembly.
Normally this door assembly is done by spot welding. Okay, is the laser welding, how it is going to help? Laser welding, normally it's going to be very, very high temperature when compared to spot welding.
Yes.
So why they have gone to laser welding instead of typical soft welding? We do spot welding.
Yeah, I think for specific regions, I think they may follow the laser-based welding. Some component, few components they'll do the.
It's only a small portion.
Yeah, it's a small, region over here, which has to be,
Okay.
I think spot welding might not be feasible at that particular locations. So that's why they're using the continuous welding.
Think up to my knowledge also, in door panels, we are using Taylor welded blanks, that different thickness materials. Sometimes one side will be 1.6 mm, another side will be 2 mm. For that, it's very difficult to go with spot welding. And also, we are going to make a butt joint, not the lap joint over here. So, butt joint, it is very difficult or impossible with research spot welding. That's why we are engaging with the laser. And also, laser is particularly pinpointing one small portion. So, heat avoidance of distortion is very, very less. So, we are going. Automation is possible. Both sides, but laser, highly possible. There are a few symptoms. Why we are going with
Calibrate and I'll come back to you.
Yes, sir. You can see not only for Taylor welded blank, it's not restricted only to the thickness. It's also with different type of material you have. First portion, you see, let us check above the partition, below the partition, let us check. Above the partition, you may have aluminum. Below the partition, you may have steel for the particular case. So that also laser is possible. Spot welding, it's very difficult. And it may
Thickness will be different.
Yes, sir.
Sometimes they go with the outer layer is going to be much more.
That is secondary for resistance spot welding. You may go for continuous seamless also. For that, the surface should be very flat. It should match with each other. But here it is not possible. And door panel, you can see different profiles. Because after the metal forming or before metal forming, you may have the welding process.
Yeah.
So it is impossible with spot welding. Only possibility is laser and arc welding. Arc welding, low cost, automation possible, but distortion is high. You do higher heat input.
Highly restricted because.
That's what. That's what only solution is laser.
So here we can see,
This is what.
So here we can see the, this particular, process, like mainly it will be done by different robots actually. Okay, here you can see the robot 1, robot 2 and robot 3, which is showing in the blue, green and the red. Okay. So mainly the robot 1 must be doing a specific area. It will be concentrating on a specific area like this. And then it will be.
I think. Can I check? Sir, no problem. You connect with college Wi-Fi, sir. Conference call Wi-Fi. You can connect, sir.
Conference.
Yes, sir. Yes. C is caps,
C.
and then remaining things he shows.
Share the screening.
Yes. Yeah, back.
Yeah. Hope I'm audible, sir.
Yes, sir. Screen also visible, sir.
Thank you. Thank you. So this is nothing but a the weld sequence in which the different robots are performing the welding simulation or the welding process actually. So we try to model that the sequence, the welding, the trajectories, those kind of parameters. We try to model it in the tool actually. Okay. So here it shows the the modeling aspects, like we created the finite element mesh, and then we input the the weld trajectory, weld path, and we try to you can say simulate this particular process as it is done over here actually, as it's shown over here. So this is studies done by the Audi, and they were able to find the simulated this thing here, simulated result as well as some measured result. So we can see the trends of the simulation and the measured result to be somewhat acceptable range actually. Okay. And we try to here model the heat source or the heat source parameters here to match the simulation and the real-time process basically. And this was study was done for different influence of distortion based on different weld seam approaches. Like if you use a continuous approach or a discontinuous approach or a staggered approach, what can be the specific outcomes of these? Okay, so this study has been done actually. So then there is a crossbar beam, which is something but an arc-based. You can see the assembly here, which is with all the fixtures, the clampings, and then the the support structure. I mean supports there for the welding applications.
Still, this is a very crazy part of the car.
Yes.
All interior dashboard has to fix on this metal fellow.
Yes.
And messy.
Yeah.
If any arm is out, means very difficult to put the plastic part assemble.
Okay.
So this was a crossbar beam from the Ford Fusion 2017, and to validate the automation of the robotic to avoid process. Basically, so here we can see you can see different areas of weldings which are there. Like we can see the temperature, peak temperatures, and then we can study you can see the stress distribution after the welding is done, and we can see the distortion patterns after all this welding is done. What is the end outcome of this? Okay, that we are able to study here actually. And then there is a B pillar welding example. So here also we can see in the B pillar, you see there are a lot of parts are there. Some 32 parts are there. Then 8 different materials are there. And the sequence is done by 6 different robots and 45 weld seams. And then total weld length seam of 2,609 mm. So like a lot of parts you can see here. And you can see the trajectories being modeled inside the software, and then how the simulation setup is done for this section. So this shows like in software GUI, like this gives a brief glimpse of the software GUI, how it looks like. Like when we do the process in increment or time wise, we can see the heat distribution or the the temperature distribution on the part actually, how the when the welding process is done, basically. And then we can study distortions which are happening due to the all these parameters. It can be the welding, the robot sequence, different robot sequence, different heat input parameters. All those things combined, it will give you the end output actually. Okay, it can be a total distortion which is happening on the B pillar assembly actually. Then another thing which is a process chain simulation of a 4. So this is actually what we are doing here is we are predicting the distortion due to welding with simufact welding and prediction of residual stresses and distribution to metal forming. Like they have done using the forming, they have formed this part, and after forming this part, they are trying to perform the welding actually. Okay, so we have a different manufacturing processes which is done to arrive at this part actually. Okay, so how do we do multiple processes? Like first we have to do a forming simulation, then we have to do the welding. And how can we capture the result which is coming in the forming, which can be some stresses or some strains which are captured in the forming simulation. And using that history, we have to do the welding actually. Okay, so that will create much more insight into the simulation because we are taking the history of a previous manufacturing process and then doing the welding simulation actually. Okay, then doing a welding simulation without carrying any history from the previous forming simulation or any manufacturing process which was done prior to this particular process actually. So outputs, they were looking at deformation and stresses and distortion due to the welding. So this was the main thing. So this was the multi-stage forming simulation. So forming simulation of form with some 11 forming stages. It can be starting from coining to cutting or Boolean operations, then stamping was done, then the bending was done, okay, to arrive at the final output like this actually. So it is something like a multi-stage forming simulation and done with simufact forming software, then including multi-directional forming steps and cutting, then final part generated by mirroring the forming result actually. So here we can see the dies or the punches and the tools which are used for the particular forming simulation actually. Okay, so once you form this particular part, then we take it to the welding setup actually like this. So in simufact welding, we can get the component like this, and then we have the fixtures, the clampings, and then all the other supports which you can use it either directly. You can import this from your CAD software, or you can use some simple geometries which you can create within the simufact to define your boundary conditions actually. Okay, so internally in the solver, all these things goes as a boundary condition. For example, your clamping fixture, your clamping forces. Okay, all these things will be going as a boundary condition inside the simufact software. So parts are assembled in the manufactured configuration. So as per the manufacturing configuration, we are trying to assemble the fixtures along with the part, along with the component, and then the setup, the assembly and clamping with large displacement can be done with the simufact welding. So after assembling this part, defining our parameters, defining our weld trajectories and weld path, we will do the welding simulation. So for the welding simulation, for example, if you do a welding simulation without the forming history and with the forming history actually. Okay, so from the forming history, some residuals result which is coming from the forming will be taken into the welding actually. Okay, so that will be something like you can see here comparison. They have made a comparison with forming history, that blue one which is nothing but with the forming history, and the red is without the forming history. So you can see the drastic change in the distortions actually. Okay, if you are doing the analysis with and without the forming history. So this will show us like brief overview on the welding, how it is done. And we can study they have studied the shape deviation due to welding distortions within the tolerances. Okay. And then there is another case study for motorcycle bike frame. So this was also done for the, bike frame component here. So here we can see the heat affected zone or the, the fusion zone we can see, which is in the software, we can get these results in such plots actually. The red area showing the fusion or the melting zone. Okay, it can be studied in the software by using the simulation actually. And here it shows a peak temperature output after the welding is done. So this shows the, you can see the meshed component here, the finite element model, which is being meshed and it is showing the result actually. This shows a result for the stresses which are coming in the components. It can be residual stresses after the welding is done. Okay. And we can study the, the different effects due to residual stresses in the component after the welding. Then comes the distortion results. We can see the results due to distortion after the welding is done. So we can see the initial configuration and final configuration after we perform the welding analysis. Okay. Next capability, like spot welding. So resistance spot welding. This is also a major capability for the automotive OEMs. So OEMs like Bajaj and BMW or these kind of OEMs are using the simufact software for optimize their spot welding aspects actually. So this shows a case study of a wheelhouse. So in the pink color, we can see the component part which is going to be welded. And then it is fixed by different fixtures actually. Okay. So you can see the fixture geometries here. So they want to study using these fixtures, what can be the outcome of the welding by performing the spot welding operation on the component actually. Okay. So these are different parameters we have to for the spot welding. That is the electrode parameter, that the electrodes will be chosen from the ISO standards, which are there inside the simufact tool. You can pick your electrode inside the, template, which is there inside the tool. And we can give the different inputs, parameters, like it can be your force, then the, the time cycles, and then the ramping time cycles. All these inputs we can give inside the software actually. Okay. So once this shows a brief overview on the GUI part, how it looks like. So while showing the demo, I'll give an overview of the GUI. So if you can see the different, spots, locations here where the spot welding need to be done. So we are modeling the, the trajectories and then the weld sequence in the component actually. Okay. So this shows the temperature output. So here we can see we are monitoring the temperature, keeping a track of the properties basically. Okay. So this will give a clear indication like whether the temperature is sufficient or whether we have to increase our parameters to get the correct fusion at that particular areas or not actually. Then we can also see different fraction of phase transformations happening, like fraction of martensite, or so you can see the martensite spots, making sure that it will have a stronger bond at those locations actually. Okay, so these are some metallurgical aspects where we can monitor to get a correct idea on the process basically. Okay, and coming to the mechanical aspect, like stress, like for example, stress levels, it is selection of the spots sequence. So whether the chosen spot sequence will give us the correct, distortion or the residual stress outputs that we want or not, that we will get an idea on the result like these actually. Then come distortion. So distortion is another aspect, like the main aspect, controlling the distortion level. So we can see the spot when we are doing like this, there are some distortion, local distortion, which are coming at that particular area. So how we can reduce this kind of distortion, whether we have to change our fixtures or whether we have to modify our parameters in the welding. So these kind of studies can be made. So this shows all the results that we can get from the welding simulation. It can be thermal result, or it can be metallurgical result. It can be a stress result, or it can be a distortion. So this shows a result in all the different aspects actually. Okay.
I have one doubt.
Yes.
So apart from these things, is there any defects we can identify by using your simulation, sir? Like cracks, like that we can identify.
Yeah, cracks can be identified based on our outputs, stress outputs, like
Like that we can identify by using the simufact, sir.
include.
Apart from that, we also consider that defects, no, sir.
Yes, sir.
That's why I'm asking.
Yeah. Welding defects mainly, we can make out cracks. This is,
Yeah, might happen, yeah.
yeah, wherever the stresses like residual stresses are coming concentrated, or we can study the principal stresses or tensile stresses. Wherever the tensile stresses are coming, there can be, possible
So
reasons of crack at the weldment region actually. Those kind of things can be studied.
It cannot predict porosity and all that, right?
Porosity and all we cannot study. Aspects we cannot study. Chemical aspects, those kind of things we cannot.
I know the which type of heat source is used in this.
Heat source. Heat source modeling, we can use a double ellipsoidal Goldak heat source model. And for laser, we have the beam heat source model available.
Gaussian conical.
Conical heat source as well as the cylindrical heat source we can model. And there are certain advanced capabilities like using subroutines. We can develop our own heat source. That kind of capabilities can be put inside the software actually to define our own heat source if you want to model. We can make use of the user subroutines and we can do that actually.
in that we can add the materials.
Yes.
Can define it.
We can define the material. We can take the material from the library. We can modify the material. Suppose if we can modify the
Percentage of elements.
yes, sir. What we can do is, for example, you might be having a material inside the library, but what material you will be having might be different grade actually. So that mechanical properties might be slightly deviating from the software mechanical properties. So that time what you can do is you can pull in this material property. You can go inside that material property and you can modify according to your requirement.
Okay.
You can bring in your scan plot from your this thing, and you can using the scan plot you can make your property, or you can bring in the Excel sheet as a column data. You can feed in the data. You can modify the existing property and save it in the database so that you can use it further for your analysis.
Thank you.
So this one, what they did is, coming further to think what they found out is here they were having some distortion, problems that was happening. So here they tried out with different, fixture actually to optimize the fixtures actually. Okay. So what they felt is some of the fixtures might not be necessary for this process. So they try to optimize the fixtures and reduce the number of fixtures basically. Okay. Which can, reduce the, total weight of the assembly as well as try to reduce the fixture, the distortion based on some location of these fixtures basically. Okay. So before that, like we can see this yellow fixtures are there that they try to remove it and they try to do the analysis or the process with the other fixtures which are there in the component here actually. Okay, so the yellow ones were cancelled from the process. So in that way, we can see that after that, the total distortion, they were able to reduce it. And with this, distortion got reduced by 70%, as well as the fixture weight of the assembly also got reduced by 25% actually. Okay, so this was for the spot welding. So this will show a brief idea of how the spot welding things are done inside the. So this is a pillar where the spots are getting done in the simulation basically. This shows different result, whatever we saw earlier, like this was a displacement or stress result. And then, we don't have to wait for the result for the entire result or the things to complete. We can see the intermediate result. As the process is going on, the result can be viewed in the GUI. For example, the first weld is done. We don't have to wait for the entire process to complete. So that intermediate result viewing is available in the GUI, which I'll be showing in a while. So this shows a rare muffler bracket case study. So this you can see a customer actually, they have shared the CAD model. For example, they are having the CAD model with them. They want to perform the simulation using the simufact welding. So this is something like a MIG welding, and this is the materials that is getting used. Okay, ASTM, these two materials, and the weld filler. You can see the DIN standard of the weld filler, and the welding parameters like current, voltage, and weld velocities. You can see, okay, and the number of robots, welding duration. All these are the input that we need inside the software actually. Okay. Then this is the entire fixture showing the part along with all the components inside that. Okay. So this entire thing we'll be getting it from our CAD software, where you would have modeled all these fixtures along with all the clamping location, along with the component, how it looks like in the CAD software. So this model we input inside the software. Okay. This GUI, whatever is shown is the Apex, MSc Apex, which is a preprocessor for the simufact welding, where here we will be doing all our welding, all our meshing as things actually. Okay. All the finite element mesh we will be generating inside the Apex tool, and any geometric, you can say, cleanup you want to do, all those things can be done inside the Apex tool. Like you want to, delete some fillets, defeature options, defeaturing holes, those kind of aspects can be done in the simufact, in the Apex software actually. Okay. So you will be getting a whole, entire assembly like this, but we need not take the entire assembly for our analysis actually. Okay. What we need is, we need the component along with the fixtures for the clamps. So there are some, this bearing means it is something like a fixture. It is not like a bearing component that we understand. In the simufact, I'll show you bearing means it is something like a table or some kind of a support on which the component is kept for the welding. Okay. So we need all the fixtures for our analysis. We need all the clamping geometries, whatever we have modeled or whatever we are going to model, that we need for our analysis. Then we need the component, whatever we are going to weld at. Okay. So you can see a bolt kind of thing here, and two other components are there here actually. Okay. So these two components will be welded, and this will be welded by a circular weld. Okay. So this is the details of the model actually. Okay. So this CAD model has been imported, and then we have segregated all our geometries which we need for our analysis. Then the next step would be meshing this component. Okay. So in the back end, it is a finite element based modeling. So the finite element model for the assembly will be generated using the MSc Apex software actually. Okay. So here we created the mesh for our component for welding. And here you can design your weld filler. If you want to design your weld filler geometry, you can make it inside the MSc Apex, or you can make it inside the simufact welding also. Both you can use it for creating your filler or weldment actually. Okay, 3D weldment. So this shows a meshed model of the assembly, which is there in the component. So this will look something like this. Once we set up inside the simufact software, it will look, so this will be your components supported by all our, fixtures and clampings. So these arrows will show you the clamping direction. So this is the one clamp is there here. Another clamp is held on the back side. And then there is a clamp which is held together in the front area. Okay. Then all these arrows and these, whatever is shown here, all these things are the weld trajectories actually. Okay. So your trajectory direction, weld path, and then angle of the robot, all these things are defined here inside the weld trajectory. Okay. So this will show the clamping, you can say the sequence. So here you have one clamping, this thing, here one more clamping is there on the top. Okay, some fixtures are there along with the clamping. Okay, and this shows the sequence of the weld direction and weld sequence. So sequence one will be a straight weld of this component from here to here. It's around 110 mm, something like this. Then another weld 115 mm from here to here. And then there will be a circular weld which will be done on the like a bolt location. Okay, so this will be the sequence of weld. So this will be the weld filler, which is modeled here. Weld filament or filler. On this, you can see the trajectory, which is modeled. So it is having around 45-degree maintained at this thing from the direction of this weld filler. So this arrow will show you the direction on which the robot will be held on the component during the welding operation. Okay. So this is a how inside the software it will look like it. So results. So results we can see as we saw earlier results. Additional to that, we can see contact status, whether all the fixtures are contacting the workpiece during the simulation, or whether some fixtures are losing the contact from the components, that we can analyze using the contact status output in the software. So this will be to analyze whether the fixture is slipping or whether any clamping is slipping from the fixture or not. So that kind of things we will get it actually. So then we can study total distortions. So here you can see the part getting distorted after finishing all this welding sequence. You can see the weld filler getting deposited on the areas, and then afterwards we can study the distortions coming on the parts actually. Effective stresses can be a study which can be made for the component which is welded. And then they show the peak temperature. So peak temperature, it gives us an idea whether all the areas have reached the melting temperature to properly melting the region in that particular zone. So if it is not melted properly, the fusion may not happen properly at that regions. So this peak temperature output will show you whether all the regions are properly melted or not actually. So this the almost the yellow color or the light yellow color will show you whether all the regions are getting properly melted. Then comes the heat affected zone. So here in this red, it will show the fusion areas. Okay. So here, if it is like more amount of energy is going in, or power is more, or something which is more than the required amount, it may go for a burnout. So it may penetrate inside the component through the thickness. It will penetrate, and it will create a more melting in that area. So we can also optimize our heat source based on the region that we can in the melt, based on the melt zone or melt area, we can get it as a heat affected zone. Okay. So this shows at different areas. So here you can see one area where the heat is penetrating through the thickness. So maybe we have to optimize some parameters in those locations.
Then the heat is separated. So we can measure the heat separation. As the heat transfer, we can identify by using this simulation. Sir.
Yes, sir. Yes. Yeah. We can identify.
Yeah.
We can get a history of the temperature.
Yeah.
A particular location using some probe. We can measure, and each and every time what is the temperature output, and also what is the heat input which is going in location.
After the welding, we can identify heat transfer also. Is it?
Yes. Yeah.
Yes,
sir. The welding time.
So after welding, after 3 seconds, after 6 seconds, after 9.4 seconds, how the bead profile is here.
Yes. After different instances of time, for example, like after 3 seconds, how is your welding fusion happening? After 6 seconds, what is happening? So it's like something like we can say thermomechanical simulation, what we are doing here actually. So we are feeding in our exact welding time, your clamping time, cooling time, everything we are trying to capture here basically. Okay. So that is what we are trying to do here now. So should we have a break or something?
Yes, sir. Next, I think most of your slides.
Yeah.
Then we go for hands-on training.
Yeah. I'll show you a demo of the software.
Yes, sir. That will be carried out in
CAD lab. Okay. Thanks.
only for delivering the lectures. We'll come here.
Come here. Okay.
So, dear participants, and we are closing our third day first session. If you have any queries, you can raise your hand. You can unmute yourself, or else you can type and drop it in the chat box. We will clarify your questions. Offline participants that frequently asking question. If any question is from online, we are welcome.
And this forming thing, shall we do it now or?
No, sir. First, one lecture is over. With respect to the lecture, we'll go and have hands-on training. And afternoon, we have one demo that lecture. Then after that, we'll go for one more hands-on. Online participants, any queries?
Sir, I have one doubt. After simulation, during the real-time product manufacturing, you facing any issues, sir? The same output coming or any differentiation or any error it is coming, sir? The company, they gave the suggestion for the output, it is after simulation, it is coming for better or any error coming?
I got it, sir. What you're asking is, what is the deviation or errors which is occurred during simulation as well as the real-time case? That is what
Yes, exactly, sir.
Yes, sir. Yes, sir. As this actually what we are trying to do here is since it is a numerical based calculation that happens at the back end. So always there will be a slight deviation from your exact experiment.
So only I am asking because during the research also, surely if I simulating something and real time, some differentiation it is coming. How you overcome this differentiation?
Sir,
based on the
finish
studies
it,
only.
sir. If finish it,
Okay.
I will answer. Thing is, while going for simulation, we should go with some assumptions, sir. In real,
Yes, sir.
those things will not come, but actually in the simulation, we are taking assumption, such as shielding gas flow rate is uniform, laminar, and Marangoni effect. Most of the simulations, if you are not interested with the fluid characterization, means you will never worry about Marangoni effect. You will never worry about the heat transfer. You will take only conduction heat transfer only you are taken. So many assumptions are there. Because of that only, we are having some deviations. And also, yes, sir. And also in simulation, you may take the exact calculation for heat input, but real-time case, we cannot achieve that much of heat input with efficiency rate. There are some few mistakes or errors are there, so we cannot match with both. But within the certain level, in the permissible level, we can match with each others. If
Yes, sir.
yes, sir. If you are
I know that, sir. So only how
Yeah.
we overcome that small error? It is any possibility is there?
Yes,
That is my.
yes, sir. Through research only, you have to go and you have to redo your work very perfectly, sir. Because for such cases, if you want to see the bead profile, and you may able to see what is the pressure and their impression on the bead profile. For that, you never worried about the temperature. You are always worried about the properties of the material under the condition. Viscoelastic, plastoelastic, some conditions you will add, right? So we cannot merge everything with one.
Yes, sir.
Such a way you can eliminate one by one, you can eliminate and you can check. Nowadays, in the papers, I'm seeing that assumptions are getting less. Previous case, 10, 15 assumptions also they will take. Nowadays, softwares are developing one by one, so assumptions are getting reduced. You have to redo or you have to go with your another software or check where it is possible. Because in console, I found that they have different type of fluids flow they have. Plasma, ionic, etc. Previous cases, the ionic flow, ionization flow is not available. You can check, you may. During meshes also, we have some extra cases with the console, and this is the first time I'm going to try with simufact. So I don't know what is with simufact. So these are all some conditions, sir, why we are unable to reach the experimental work with simulations.
Okay. Thank you, sir.
So any questions, sir? Any questions from participants? Now we are wind up our third day. First.
Sir, you offering any courses for SimFact in your company, or you conducting any internship?
In the company,
Yes.
For the training purpose, we're not conducting any training purpose, but we are giving hands-on trainings like this faculty development program concern. So
Because in that faculty development program, very short duration is there, very difficult to learn more, sir.
we have a training, it's a paid training session we are conducting that we can discuss later. I connect with you later and we'll discuss on these further steps.
Okay, thank you.
May I know your name, sir?
Sir?
May I know your names and name?
Myself, Manigandan, sir.
Manigandan, okay.
I'm from Welltech Research Scholar.
Okay.
Sir,
okay, no
your
problem, sir.
presentation is good, and I have some clear idea about the software also. Thank you, sir.
This is a very well-worth GUI software. You can learn as quickly as possible. There is much no complications are available like FEA analysis software.
Okay, yes, sir. Thank you.
I'll demonstrate.
Okay, thank you.
Here, Manigandan, you are always welcome to NIT Puducherry. Tomorrow also we have hands-on training session. If possible, you can come and you can have a hands-on training session by tomorrow also. Or else you drop a message in the WhatsApp group. We will give the contact to simufact services. And if they're conducting any FDPs or workshops, they will call you. That's why we can do some help.
Okay, sure, sir. Thank you very much.
Thank you.
Thank you, sir.